Okay, in this video I'm going to be continuing our work on introducing energy, and I want to talk specifically about the principle of conservation of energy, which says in a conservative system the change in potential energy plus the change in kinetic energy is zero. In other words, the total change in mechanical energy is equal to zero. There's no loss in energy in a conservative system. An example of a conservative force is gravity. Gravity is not removing energy from anything. It's changing things, but it's not removing energy from a system. A non-conservative force would be friction, because friction will remove energy from a system. If I drag a sled along the ground, I'm generating heat, it's generating sound, there's energy going away from the system in other ways. I want to think about, let me get rid of this. I just want to think about, an object, maybe a ball that I drop from a height. Okay, so if I hold this ball here at its initial position, suppose initially this is at rest. So we've got an object here that's initially at rest. If I think about what's going on here, and suppose I just make up a number here. Suppose I say, this object is 100 meters off the ground. If it's at rest, what's its kinetic energy? Well, its kinetic energy is a half times its mass times the square of its speed. If it's at rest, its speed is zero. So at the moment, its kinetic energy is zero. Okay, so this is an object that's held at rest 100 meters above the ground. Its potential energy would be its mass times g times h. Its height here is 100, so it'll be 100 multiplied by whatever its mass is, multiplied by little g. And that'll be in joules. Now, what happens as I release this object? As I release this object, if I release an object from rest 100 meters above the ground, what's going to happen? Well, what happens is it accelerates towards the ground. In fact, it accelerates towards the center of the earth, picking up speed as it goes. As it's going along, it's picking up speed. That means its kinetic energy starts to increase because its speed is increasing. So as it's moving down, what's happening? Well, its kinetic energy is increasing. Now really think about what that is. Well, because its kinetic energy is dependent on speed. Its mass isn't changing, but its speed is. So its kinetic energy is increasing as it's moving down. It starts from rest, it accelerates towards the center of the earth until it hits the deck. As it's moving down, what's happening to its potential energy? Well, its potential energy is based on mg. The m will be constant, g will be constant. Its height will be changing, so it's dependent on its height. As it's moving down, its height is decreasing. So its potential energy will be decreasing. And what we have here is a kind of a transfer of energy from our potential energy into kinetic energy. And what happens when it hits the deck? Well, when it hits the deck, at that instant, not an hour later when it's sitting there on the ground, I'm talking about the instant it hits the deck, its height, its potential energy, which is based on its height, its potential energy when it hits the deck, will be zero, because its height will be zero. All of its energy now will be kinetic. All of its energy will be kinetic. And spoiler alert, that kinetic energy is going to be that quantity there, 100 mg. Guaranteed. Because there will be ultimately the total change in energy is zero. So its total energy at the final position should be the same as its total energy at the initial position. We could use our old master equations of kinematics to show this. What would its speed be as it hits the ground? Well, we know V is equal to U plus AT. We said U was equal to 0. Initially it was at rest, so V is just going to equal to AT. A is equal to G. In fact, a better equation to use here might be V squared equals U squared plus 2AS. I use that equation instead. V squared equals U squared plus 2AS. So U is equal to 0, so we're going to get V squared equals 2AS. So V squared is going to be 2 times G is A, and S is 100. So V squared, the square of its speed here, is going to be 200G when it hits the deck, using my master equations. If I think about my kinetic energy, it's a half times mass times V squared, where mass is constant, and so it's going to be half of V squared. If V squared is 200G, half of 200G is 100G. So again, 100G times M, or 100 mg joules. But I knew that anyway because I know the principle of conservation of energy, which says the total change in energy is 0. So what happens, and again, think about it, it starts at rest 100 meters off the ground. It has no kinetic energy. All its energy is potential. As soon as I release it, its kinetic energy starts to increase. Its potential energy starts to decrease. And again, think about why that is. Until finally, at the instant it finally hits the deck, its potential energy has been reduced to 0 because its potential energy is based on height. So its potential energy there has been reduced to 0 because its height has been reduced to 0. All of its energy is kinetic. I know that the total change in energy is 0. So all of its energy has to add up to 100 mg, so its kinetic energy has to be 100 mg. I could, of course, as I did here, use my master equations of kinematics to find V squared and to work out the kinetic energy, but it's a little bit, long-winded. At some stage along here, I don't know where, but at some stage, if its kinetic energy has increased to 25 joules, I guarantee that at that moment its potential energy will be 75. Mg. I'm leaving out my units here. So at some stage, if its kinetic energy is 25 mg joules, well, its potential energy at that moment would be 75 mg joules. I know that because its total energy is 100 mg joules, so it's not changing. As it goes down, a little bit further down, where, I don't really know where, but suppose at some point its kinetic energy will have picked up to be 60 mg joules. At that moment in time, its potential energy will be 40 mg joules. How do I know that? Because its total mechanical energy is constant at 100 mg joules. Mechanical energy is the sum of kinetic and potential. Eventually we'll get down to the bottom, and right at the bottom we have this situation where its potential energy has been reduced to 0. Its kinetic energy is 100 mg. Okay, so the principle of conservation of energy.